Welcome to qnawire.
This is problem 62 of chapter 23. For this problem, we're asked to analyze a glass wedge of a certain refractive index where a 5 nanometer wavelength of light is shined onto it, and we're looking for the thickness of the wedge such that constructive interference occurs. So let's go ahead and write down what we know. We know the refractive index of air. We're going to write that down as 1.00. We have the refractive index of the glass. This is given as 1.64. The wavelength is lambda equal to 500 nanometers. So this is equal to 500 times 10 to the negative 9 meters. Let's go ahead and draw our wedge. So we have a horizontal surface on the wedge. Here is the height of the wedge, and then it comes all the way down here. Now this wedge is coated here at the bottom, so it's coated with silver at the bottom. And what that's going to do, that's going to cause a reflection. Once the light hits this glass silver interface, it's going to reflect away. Okay, we're also given the height of the wedge as 1 times 10 to the negative 5 meters. And what we're looking for, so this is here the silver coating at the bottom of the plate. What we're looking for is the distance from some origin. So if we take our origin here, we're looking for the distance from this origin to some position here, x, such that when light comes here and it reflects, there's going to be constructive interference. So let's go ahead and draw a light ray diagram. One more thing that we should write before we start is that the refractive index for silver, well, since it's going to be reflective here, that refractive index here for silver, once it bounces off of silver, it's going to experience a pi degree phase shift, okay? Pi radian phase shift, or 180 degree phase shift. So let's start with the ray diagram. So as light is coming in here, it reaches the interface between the glass and the air. Since it's going from low to high, the reflected light from this interface is going to be shifted by 180 degrees, or is going to experience a pi shift. So 180 degree shift. Now that corresponds to a path length difference, delta ref. Okay, so here this is delta reflection. This is going to be equal to lambda over 2. So light comes here, it strikes the glass. Since the glass has a higher refractive index than the air, the reflected light gets shifted by 180 degrees, and that corresponds to a path length difference of lambda over 2. Okay, the light that's transmitted continues to go here, this distance d. So it's going to be a distance d. Now keep in mind that this wedge is very thin, so even though I'm drawing it at an angle here, the light is really going to come down here, like so. Like so. So actually, let me go ahead and rearrange this orientation of the light. So as the light comes in, here it's going to get reflected, and then part of it is going to get transmitted. Here it is transmitted. It's going to travel this distance d here, and then part of it is going to get here. It gets reflected because of the silver coating, and when it gets reflected, it's also shifted 180 degrees. So there's another shift of delta ref. delta ref for reflection. That occurs here at the bottom interface of the glass. And then the light is going to continue to move through the glass and then eventually out through it, like so. So we're looking for this thickness here, D, such that these two reflected rays constructively interfere. The net path length difference, we're going to symbolize that with delta. This is going to be equal to the path length difference associated with the first reflection, so delta ref, plus the path length difference associated with the light going through the glass wedge, so we're going to call that delta T. And then we have another pi shift with its associated path length difference here, so delta ref again. For constructive interference, the net path length difference must be equal to some integer multiple of wavelengths, lambda. So in this case, m is going to be equal to 0, 1, 2, 3, etc. So an integer multiple. But since these are non-zero quantities, we could go ahead and start at 1. 1, 2, 3, 4, because there's this thickness here is going to be non-zero, so there's no way that this could be equal to 0. So here we are starting at 1. Now let's go ahead and make some substitutions here, because each delta ref, or the path length difference associated with a 180 degree phase shift, is lambda over 2. We can make this substitution in this equation. So let's go ahead and do that. We have delta is equal to lambda over 2 plus delta t plus another lambda over 2. Is going to be equal to an integer multiple of lambda. Notice that this lambda over 2 and that lambda over 2 combine, so we have lambda plus delta t is equal to some integer multiple of lambda. So that tells us that delta t must be equal to some integer multiple of lambda. Now the important thing to note here is that the integer multiple of lambda that delta t has to be equal to is in reference to the wavelength of the light in the material. So in this case, it's the wavelength of the light in the glass. So we're going to call that lambda glass. And delta t, the path length difference of the light as it goes into and then out of the glass again, is going to be 2t, where t is the height of this triangle. So notice that here, the way I drew the diagram, this t does not equal this one, but in reality the light is going to come in and then out back where it came from once it's reflected. So this is just for illustration purposes. This length is actually equal to this one here. So that's why it's 2t, and this is going to be equal to m times lambda glass. So let's go ahead and solve for that thickness here. T is going to be equal to m lambda glass over 2. So the minimum distance, T min, is going to occur when this quantity is minimized, and that occurs when m is equal to 1. So here we have m is equal to 1. 1 times lambda glass is just going to be lambda glass over 2, like so. Next, so a point needs to be made here. Here, lambda half plus lambda half is equal to lambda. So lambda plus what is going to give us integer multiples of lambda? So that's why delta t has to be equal to lambda times m here. M lambda glass. This m is this same m for this example. So depending on the problem, this would change. For example, if this was destructive interference problem or something else, or if we didn't have the double phase shift here, then this would have to change. So make sure to analyze these situations carefully. Okay, so this is T min, lambda glass over 2. Now we have to solve for lambda glass. To do that, we are going to have to look at the refractive index of glass. So that is n glass. And this is defined to be speed of light over the speed of light in the material. So in this case, it's in glass. Let's go ahead and rewrite the speed of light as lambda, the wavelength of the light in air or vacuum, times the frequency of that light over v of glass. Okay, what I'm going to do now is I'm going to solve for v of glass. V of glass is going to be equal to lambda f over n of glass. So this is done by rearranging this equation here. I could take the reciprocal of both sides and then multiply both sides by lambda f. That's how we get this. But velocity of glass, that's just going to be equal to lambda glass times the frequency. And the frequency is determined by the source. So these two f's cancel out, and then we get an expression for lambda glass. Lambda glass is going to be equal to lambda over n glass. Now I could go ahead and substitute this expression into this one for T min. So this is going to actually be lambda, no subscript, over 2n glass. Okay, so this is our thickness. This is our thickness, but that's not what the question is asking. The question is not asking for the thickness, it's asking for the distance x, such that the thickness experienced here by the light results in constructive interference. So if this is the thickness, let's look at the geometry here. If this is our angle theta, let's go ahead and label this angle right here in red. If this is our angle theta, notice that we can say tangent of theta is going to be equal to that thickness t over x. Well, it's actually t min over x. But that same angle theta is going to be equal to this height of the wedge over the adjacent to the angle, which is the length of the wedge. So the length of the wedge is given in the problem as 0.20 meters. So the whole length here, let's go ahead and label that. This whole length from start to finish here of the wedge is 0.20 meters. That's this length here. So notice that due to similar triangles, opposite over adjacent here between this height of the wedge and the length of the wedge is equal to t over x. So let's go ahead and move the x right underneath the t there. And let's go ahead and put 0.20 here. Okay, here we can go ahead and solve for x. Again, let's take the reciprocal of both sides. If we take the reciprocal, we get x over t min is equal to, notice that the units cancel out here with a meter, so 0.20 over 1 times 10 to the negative 5. Now we solve for x. X is going to be equal to this fraction times t min. And we know what t min is because we solved for it here. So we could go ahead and substitute this for t min. Let's go ahead and do that. Let's grab t min here in terms of lambda and n glass. And now let's plug in all the values. So this is going to be our final answer here. Once we plug in all the values, let's put a box around that. Let's go ahead and copy all this. And what we're going to do now is just replace the values. So here for lambda, we have 500 times 10 to the negative 9. And here for n glass, so 2 times n glass, and n glass is 1.64. So here in the numerator, this is in meters, so our overall unit is going to be in meters. So let's see what we get. So everything here multiplied out comes out to be 3.0 times 10 to the negative 3 meters times 10 to the negative 3 meters. Okay, let's make some space here. So 3 times 10 to the negative 3 meters, that is just equal to 3 millimeters. And that's our final answer. So if we go 3 millimeters away from our starting point here, we're going to have a thickness such that the reflected light is going to constructively interfere. So that concludes this problem.